Okay, hello and welcome back. In this section, we'll cover 2.3, continuation of looking at properties of functions. So we'll go beyond thinking about just like intercepts, things like that, and we'll think about like the behavior of functions over certain intervals or over their domain. So that will involve, does it have some kind of symmetry that'll be even or odd behavior? Um, Is the function increasing or decreasing or constant? Does it have any local minima or maxima or absolute minima or maxima? Um, and we'll end looking at the average rate of change of a function over a given interval. So we're getting to analyze some behavior of functions, both by looking at their graph and also analytically just looking at their formulas. So let's start with thinking about symmetry. This is identifying an even or odd function. So let's look at the definition of an even function. It says a function f is even if for every number x in its domain, meaning across its whole domain, the number negative x also being in the domain gives this relationship. This means when you plug in the negative version of whatever the original input was, you get the same output. F of negative x is equal to f of x. This causes a symmetry across the y-axis. We plug in some negative version. If this is our x, it has some output. Plug in the negative version, it would be equal to that same output. Let me give probably a simple example. The one that I always like to use for an even function is x squared. So if we draw this, it's a parabola centered at the origin. Let me stick a few points. So I know its center is at the origin. F of 0 would be 0. If we plug in 1, we get 1 squared, which is 1. And if we plug in negative 1, notice we also get 1. That is that kind of behavior. So the squaring just undoes the negative for us. So this will be our graph. So in general, this is where x is greater than 0. This is your positive x values, and this is where x will be less than 0. And we can see there's this symmetry. Imagine a mirror going down the middle of the graph. So visually, we can recognize it by having this symmetry across the y-axis, and it has this kind of behavior. F of negative x will equal f of x. And just to show again, let's imagine we have 2. So this would be 2 squared, which is positive 4. Or if we plug in negative 2, we would have negative 2 squared, also positive 4. So f of negative x equals f of x. So I'll just add that even functions are symmetric across the y-axis. So let's consider something different. So this would be an odd function. So for an odd function, we get this pattern where we're saying f of negative x equals negative f of x. Meaning when we plug in the negative version of our input, we get the opposite sign of our output. So let's see an example. A simple one here would be x cubed. So we'll say f of x equals x cubed. So let's look at this one. And if we do a similar thing, let's use 2 and negative 2 again. Say we have f of 2, well, we're doing x cubed this time, so this is 2 cubed. So that will be positive 8. And then if we plug in negative 2, you get negative 2 cubed. So 2 times negative 2 will give us positive 4, but then we multiply by another negative 2, so that will give us negative 8. So the outputs have a flipped sign whenever we change the sign of the input. And that will be that property. F of negative x equals negative f of x. And so visually, I know here 0, 0, we can do 1, positive 1, negative 1, negative 1. And if you recall, x cubed looks like this. So they call this kind of symmetry being symmetric about the origin. And that's what they're throwing in down here. So to be symmetric about the origin, imagine if you first took what is on the positive side of the x-axis and flip it across. So flip it across the y-axis and then across the x-axis. So imagine taking that part of the parabola, flipping it over that way, so it looks something like this, and then flipping it across the x-axis, and then we get that downward shape. So it's symmetric about the origin. Odd functions are symmetric about the origin. So visually you can think about this like double reflection across the y-axis and then across the x-axis. So just to practice looking at a graph and determining if a function is even or odd, let's just think about that symmetry. So on A, we've got an upside down parabola. It is a mirror image across the y-axis. Think of some positive x, and then that same one on the negative side, we get the same y value, the same point, or the same height at least. So we'll call that one even. And then for B, it's not symmetric about the y-axis, because otherwise we would get something like this, like a W. If it was symmetric about the origin, I would imagine first going across the y-axis and then across the x-axis. So we would imagine it would look something like that. It would be some kind of broken function with a curve. Oops, it's double curve. So in this case, it would be neither even nor odd. So functions can be in a neither category. It's only some functions that are that have these symmetries. This function still has a symmetry. You can imagine drawing a diagonal line like this. You can see some kind of symmetry there. But it's not the x-axis or the origin. So this would be neither. For part C, it's not even because then it would look like this. If it's odd, well, yeah, we would first flip it across the y-axis and then down. Now that looks symmetric down over the x-axis. So this one has the odd behavior. It's symmetric about the origin. So it's helpful to see the graph, then we can just think in terms of symmetry. But let's say we're not sure exactly what the graph would look like. We can do this analytically, meaning just looking at the equations. So let's see what we got. So my strategy here is to plug in negative x to find f of negative x and simplify, and then see if we get that kind of behavior where if we get the original function back, then it will be even, and if we get the negative version of the function, then it will be odd. So let's see what a few of these will look like. Start with A. So here our function is x squared minus 5. I'm going to plug in negative x. So I'm going to find f of negative x. So this would be negative x squared minus 5. And when I say simplify, it's usually working with these powers to see if the power essentially deletes the negative or if the negative will persist. And in general, even powers will delete out the negative. And notice this will generally associate with even functions. So there is something to that there. So yeah, notice here, negative x squared, well, that negative will be canceled because negative 1 times negative 1 is positive 1. And so we just get our original function back. Notice that these two are the same. So I'll just say this is equal to f of x. F of negative x equals f of x. It's an even function. So I would expect if I were to graph this that I'll get symmetry across the y-axis, across the vertical axis. All right, next up is B. So this says g of x is equal to x cubed minus 1. So let's plug in negative x. So g of negative x will be negative x cubed minus 1. For odd powers, it's going to preserve the negative. Imagine we have negative x times negative x times negative x. On the first two, those will cancel, and that will give us positive x squared. Then we're still multiplying by a negative x, so it's going to pick up that negative, negative x cubed. So this will become negative x cubed. So that did flip in sign, but we still have this minus 1. So it didn't quite give us the full negative version. If it was going to give us negative g of x, just for an idea of what we would be looking for, that would be negative, like a negative 1 multiplied by every term. So we would be looking for negative x cubed plus 1, because these two negatives would cancel. So since we still have this minus 1, this is a case of being neither even nor odd. So I'm going to say neither. We would need every term to change in sign. So I think in C, that's what we're going to witness. Let's look at h of x equal to 5x cubed minus x. So let's plug in the negative x. This will be 5 times negative x cubed minus negative x. So we said earlier the cubed, that will produce the negative, so we'll get negative 5x cubed, and then the double negative here will make this plus x. So notice the sign of every term has flipped. We could even factor out a negative 1, and that will make it negative 5x cubed minus x. And then here, it's easy to see that's just our h of x again. So this will give us negative h of x. H of negative x is equal to negative h of x. That's our odd behavior. And then our last one, part D. This is capital F of x equal to the absolute value of x. So let's do the same thing. F of negative x, we would plug in a negative inside. Well, the absolute value is just going to turn that negative into a positive. We can imagine this as absolute value of negative 1 times the absolute value of x. So this will be equal to just the absolute value of x, which is equal to our original function. So this is even. And if you recall just what this graph looks like, absolute value, you may remember, is like a V shape at the origin. It's definitely symmetric about the y-axis. Get a mirror image. So in general, that's the strategy. Just plug in negative x and simplify. And if it's being hit with an even power, it'll essentially delete the negative. Notice for our odd function, we had x's with all odd powers. We can imagine that's a power of positive 1. All right, let's see if there's more. So in the third section, let's look at a graph, and now we're going to see where a graph is increasing or decreasing or constant. So are the values getting larger, like the output values, or are they getting smaller, or are they staying the same? That's essentially what these questions are asking. So a couple of quick definitions. The first one says a function is increasing on an interval I if for any choice of x1 and x2 in I, with x2 being greater than x1, meaning it's like farther to the right, the output of your second x is greater than the output of your first one. Just to show this visually, imagine some graph, and our function is increasing. And we'll just look at this interval here. So yeah, for any point x1 and x2, f of x2 is greater than f of x1. Another way to see that is just if you were to trace with like a pen along the graph, and you're going up as you go from left to right, you would always go from left to right. That says the x's are increasing. Yeah, if you're moving upwards, that's an increasing function. So in the same way, it's decreasing if the opposite is happening. If we have some function, let's say now we're looking at this. Now this will be our x1 and this will be our x2. So f of x2, the y coordinate, is less than f of x1. Just to visually show what they're saying in terms of these symbols in this notation. And then it's constant if on the interval all of the x values are equal, or all of the f of x values are equal. So all of the outputs are equal. So constant would be a flat horizontal line. So imagine now this is our graph. Here's our x1 and our x2. F of x1 is equal to f of x2. So always just think in terms of going from left to right. Is the graph going up? Is it going down, or is it staying the same? So let's look at this example. So it's asking where is it increasing, where is it decreasing, and where is it constant? So let's first look for increasing, behavior. Well, let's just look at the graph in general. If I'm tracing this, I'm like tracing it downward here on this interval from -6 to -4. But then it changes and it starts to go up, continuing to go up until 0. So upward. Then we get a nice constant flat interval. And then after that, it decreases down until we get to +6 on the x-axis. So let's just split those up into intervals and list them out. So let's start with increasing. I can say my function is increasing looks like just on this interval. So it's an interval of x values. So we're starting here at -4 all the way up until 0. So I'm going to say on this interval. So just a quick word on notation. I use this open interval notation when I'm discussing intervals of increasing and decreasing or constant behavior. Because we're talking about, when we think about increasing or decreasing, we're thinking about relationship between 2 points. And it's always some interval around those. Because if we're thinking just in terms of this endpoint, say at -4, from the perspective of only looking on the right side, you could say that it's increasing. However, if we're looking on from the left side, you might be saying that it's decreasing. So for me, I don't include the endpoints because actually at this point, at -4, um, the function is not increasing or decreasing. It's sort of somewhere in between, and that's something that you'll be looking for later on in calculus, those points. We'll look at those in this section too. That's a minimum. That's a relative minimum here. And actually in terms of this function, it would be an absolute minimum since it's the lowest point out of the whole function. But I say this because I noticed in the textbook they will use a closed interval. They would say from -4 to 0. So just as a heads up, I don't know if in the homework they're going to be looking for a closed interval specifically. The way I've learned this, I've learned to use open intervals for intervals of increasing or decreasing, just because it's going to end at some edge point, and you don't know the behavior beyond that edge point. So I'm going to use these open intervals here. All right, so increasing from -4 to 0. How about decreasing? So we get our first decreasing interval from -6 to -4. And then it looks like we're also decreasing from +3 to positive 6. So we get two intervals of decreasing behavior, and I'll join them together with the union. So from 3 to 6. And then it's constant on this little interval here, so from 0 to positive 3. And just to speak a bit more on the open or closed interval, I understand where the textbook is coming from because of how this is defined. They're saying specifically on any interval, so not specifying open or closed, and then specifically where your second point is greater than your first point. That's what you're comparing it to. So if you do use an edge, so say like -4 for x, the only other point that you can compare it to is something um, to the right of it, so something that is greater than -4. And so yeah, any point that you can pick to the right of it will be given output that is greater. So I can see why they're including that edge point, but something about that feels a little bit strange to say that we're going to include -4, since technically at that specific point, I would not say that it's increasing or decreasing. But more on that later. So I mentioned in that last example this idea of maxima, minima, and maxima. So let's use a graph to locate these special points. This is something that you'll find a lot in calculus. You'll find a method for locating these points just by looking at the equation. But for now, we'll need to look at the graph in order to identify them. So a couple of definitions. So we have f as a function defined on some interval, and c is some number in the interval. So c is somewhere in the location that we're looking at. So the first definition says a function f has a local maximum at a point c if there's an open interval in I. So I is typically the domain. We're looking across the function, but it could be some subset. So an open interval containing the point that we're looking for such that f of c is less than f of x for all x in this open interval. Visually, what this means is we have, let's call this our open interval, and let's say our function is behaving something like this. And this is our point c in the interval. Well, there's this point here, f of c, that's greater than all other points. It's like at the top of a hill. And this function could continue and then maybe end up going to a higher location eventually, but we're just looking at this little zoomed in area. If we can create some little box around it where it is the highest point, then it's going to be a local maximum. That's where that local term is. And I've heard this also described as relative as well. It's a relative maximum compared to its surroundings. So conversely, a minimum still also on some interval, but then let's say our function looks like this. And this is our point c. This would be f of c. So in this case, f of c is lower than every point, than every other output in that little window. So that'll be our local minimum. So local minimum at c if there's an open interval in I containing c such that the output at that point is less than the output of all other values in that interval. So that'll be a local minimum. And just to distinguish, we would say f of c is the maximum value when x equals c. So c is the location, the x value that produces the output, which is our actual maximum value. So just keep an eye out for that terminology. Are they asking for the location of the local maximum? That would be that point, that x point, but the local maximum value is the output, f of c. So same thing here. C would be the location of the local minimum, whereas f of c is the local minimum value, the actual output value, that lowest point that it gets to. So let's look at this example and look at a graph, determine some of these points. So it asks us for part A, at what numbers at what numbers x, if any, does f have a local maximum? And then it wants us to list the local maximum values. So I'm looking for those like that hill shape, like what we were looking at here, some kind of top of a peak. And I do see we have one. You can imagine our little window around this point. Even though the function gets higher up here, we can create an open interval around, say, like from 0 to 3. And we can see that it has a local maximum there. So I would say that there's a local maximum at an x value of 1. That's the x part of this coordinate. And then our maximum value, we can say f of 1 is equal to 2. 2 is the local maximum. And then anywhere else, notice that this function continues infinitely in both directions. So even though we have some higher points here, we can't really state it as a local maximum, because if we were to create a little window around it, there's always going to be another point that's higher than that point. So for B, let's do the same thing for the minimum. So we're looking for this situation. It's like at the bottom of a valley. And so it looks like we have 2. There's one here. If we create a little window, there's the lowest point. And we have another one here. Same thing, create a little window, some open interval, and it's going to be the lowest point on that interval. So we have a local minimum The first one is at an x value of -1, and the minimum value is +1. That's the y value there. And then we have a second one, so another local minimum at an x value of +3, and the output is 0. So one local maximum and 2 local minimum. And it's easy to pick out if we're given the graph. All right, in part C, it asks us to find the intervals on which f is increasing and to find the intervals on which f is decreasing. So taking a look at the graph, even though we see this arrow here, it's tending to imagine increasing behavior because, yeah, it's getting larger. But remember, we are always looking, like we're scanning from left to right on the graph. So if I have my pencil on the graph and I'm going from left to right, it is decreasing. It's getting smaller up until that minimum, and then it starts to increase again to that maximum. Then we get decreasing again to that minimum, and then increasing infinitely after that. So notice it changes behavior around these minima and maxima points. So let's first start with increasing. I can say my function is increasing on which intervals? I think we have two. So from -1 to +1, from -1 to +1, and then it's also increasing from +3 onward. So I'm going to join this with 3 to infinity. And then we'll do decreasing. So I'll say decreasing. Now here, this continues, so we could say from -infinity up until -1. And then our second decreasing interval was from 1 to 3. So yeah, if I were to just think about a number line, and if I were to place our points where it's changing from decreasing to increasing, it happens at these local minima, like we have, and the local maximum. So we had a local minima at -1, and then a local maxima at +1, and then another local minima at +3. I could draw something like this, like it's decreasing, and then it changes to increasing, then it changes to decreasing, kind of flips back and forth, and then increasing from that point forward. So again, this is part of why I'm hesitant to use the brackets when I'm describing intervals of increasing and decreasing, because what is happening at -1? It's changing. It's going from decreasing to increasing. So again, more than that once you get to calculus, you'll be able to use some methods involving the derivative to locate these points. They have a particular location that you can find. But for now, we'll rely on the graph and just think about zooming in, creating little windows around these points. And you're really just looking for those like peak and valley kinds of locations. That's where we're switching from decreasing to increasing or from increasing to decreasing. And if we're working with functions that describe some kind of real phenomena, those are probably points of interest. Those are points you would want to know about. Where is it going to change behavior? Especially if this is some kind of financial thing. Where am I going to go from losing money to increasing money? Or what's the maximum point that I probably want to sell at? Because after that, the value is going to go down. So just to give some examples. So that was local. Let's talk about absolute, minima, and maxima. By absolute, they mean like the highest or lowest point of a function on its domain, or at least on some interval that we're interested in. So this is absolute, absolute minima and maxima. So they define it like this. They say, let f be a function defined on some interval, and a lot of times this interval is the domain. So it's defined on the interval, which is its domain. If there's a number in that interval, and they call it u, for which the output f of u, the output when you plug it in, is greater than f of x for all x in that interval, for all other points. So now we're looking from like a global scale. I've also heard this called global maximum and minimum. Then f has an absolute maximum at that point, at u. And then f of u is the absolute maximum value. And then similarly, if there's some other point, they use a v this time, for which the output, when you plug it in, is less than the output of all other values in that interval. Then we have an absolute minimum at that point, and then this output value is the absolute minimum value on that interval. So let's look at a few of these graphs and try to determine what we've got. So they give us a series of graphs. It says to find the absolute maximum and the absolute minimum if they exist. And then also to locate any local maxima and minima. So let's go through one at a time. Looking at our first one. So what do we have? This time our function doesn't go on forever. It's sort of bounded at these edges here. So when looking for absolute minima and maxima on an interval, it is important to consider the edge points because they may not occur at one of these hills or valleys like we've been used to looking for relative minima, maxima. They might occur, like the absolute highest point might occur at an edge point. Like we'll see that here in this case. That is the highest point where this function is defined. And then we'll also look out for where the function is defined itself. Notice there's some of these that have holes in them, so we'll need to consider that as well. Let's start with the first one. So does it have an absolute maxima? Is there a point that's higher than all other points on this interval? And yeah, that's actually happening here at that point 3, 6. So I can say we have an absolute maxima at that point 3, 6. I'm going to just list the point, but if they're looking for where it occurs at an x value of 3, and the absolute maximum value is positive 6. This also fits the definition of a local maxima as well. So we can also call this a local maxima because we can build some window around it, some open interval around that point, and it's the highest point in that interval. So something can be both a local maxima and an absolute maxima. So at that same point. Now, where's the absolute minimum? It looks like we have a local minimum here. There's our little valley, but there is this point at the edge of our defined interval that is lower than that point. That's going to be the absolute. So I'll say absolute minima at this point 0, 1. So 0 is the x location and 1 is the minimum value. But we also have this local minima. Here, if we have a little box around the point, the x point 4, when x is equal to 4, we can create an open interval around it where it is the lowest point in that little zoomed in picture. So it's a local minima, and I'd say at 4, 4. So minimum location when x equals 4, and minimum value of 4. Now here, I called this absolute maximum also a local maximum because we can create this interval box around it. I can't do the same thing because this point is on the edge. I can't create an interval around it because we only have the right side. I cannot produce an interval, an open interval around it. So if it's on the edge, you couldn't claim it as a local minima or maxima. It'd be a little tricky. All right, let's look at B. Do we have an absolute maximum? Yeah, it looks like at the edge, that'll be the highest point on our function. So I'll say absolute maxima at 5 comma 4. Or I'm sorry, at 5 comma 3. I was looking at the wrong one. So over here. But no absolute. I'm sorry, not absolute. Or there's no absolute minima in this case. Let me say that. Let's go back and look. So we had the absolute maxima. Yeah, there's a point that's greater. It's higher than every other point. We do have this point. It looks good. It looks like a minimum point. Looks like a local minima and also the absolute minima. However, it might be hard to see, but they have an open circle there, which means that the function is not defined at that point. So that point is not on the domain of the function. That's another way to say that. So we'd have to not include it. Well, that causes some complications because that means we would have to pick some point like barely just next to it. But if we were to consider that as a minimum, there's always going to be, let's imagine this is our open point, and there's always going to be like a little extra space in between where the function is going to be slightly less. Even if we zoom in super close, we can imagine zooming in closer, and we can see there's more space next to it. Um, there's a kind of infinity there, getting closer and closer to that undefined location. And we could always find a point that's lower. The actual lowest point that we could get to is not on our domain of the function. So we're forced to say that there is no absolute minima. That's what I was starting to write earlier. Yeah, no absolute minima because it's not defined there. Any point on the function gets lower and lower and lower as we get infinitely closer, and we can always find another point that is lower than the point that we're looking at. We'll just get a little bit closer to that undefined location. And then, yeah, so no absolute, and we can't claim these as a local, like I can't claim this as a local maxima because I can't create an interval around it. It's on the edge. And same thing here. Can't call that local maxima because I can't produce an open interval around it. It has to be an open interval. All right, let's look at part C. Put it down here. So what would I say? Let's think first about absolute. It looks like at the edge again, that'll be our absolute maxima. So absolute maxima at 5 comma 4. Location is x value 5, and then the absolute max value is positive 4. And for the same reason I can't claim it as a local maxima, how about absolute minimum? Well, our minimum, notice this is constant here. Our minimum occurs for every x value in that interval. So I can describe that here. So absolute minima, um, the value is 1, so I can say it this way, absolute minima of 1 when, and I'll use a little notation. I'll say x is an element of, that's what this little e means, this interval from 1 to 2. So anywhere if x is 1 anywhere up to where x is 2, it will have that output minimum value of um, positive 1. And that's what we see on the graph here. So there's infinite number of locations where that minimum is occurring. And then we can call all of these points local minima as well. Because if we take some point, we can produce an open interval around it where it will be the lowest point there. So I'll just say also local minima on that same interval. And just want to look, see. So it's part C. Yeah, local minima on that same interval. Okay, so that was our local. Does it have a local maximum? Kind of the same as before. We can't call this a local maximum because it's on the edge. Can't build an interval around it. All right, let's try to squeeze everything in here. For D, D starts at the origin, then just continues to increase infinitely after that. So what can we say? Can we claim an absolute maximum? Well, anywhere we place a point, there's going to be a point to the right of it that's greater, and that continues on to infinity. So definitely no absolute maximum. And for the same reason, no local max too. It does have this absolute minimum where our function is starting, so at 0 at the origin. So absolute minimum at 0, 0. And because it's on the edge, we can't claim it as a local minimum. Can't build an interval around it. So no local min. And then what about for E? I'll squeeze that in here. Does it have an absolute maximum? Well, I see here there's an open circle at the edge, so they're saying that the function is not defined there. So again, we can zoom in infinitely closer. We can pick some point close to it, but there's always going to be another point above it. So we have to say no absolute max. But what about a local maximum? Well, yeah, we have one here. We can create an open interval around that little hill. So I'll call that my local max. So that's at 4, 3. So location x value of 4 and the local maximum output value of positive 3. And then looks like we would have a local minimum here, but it's undefined. There's an open circle, so I can't claim a local minimum. And in the same way, there's no absolute minimum, because notice here, this continues on infinitely towards this asymptote, so it's going to keep getting infinitely lower as we approach the edge there. So no absolute minimum, there's always going to be a lower value. and no local minimum because this is an open interval here. So it might get slightly technical in this, defining if it's local, a local or absolute maxima, when can you claim it as a local one? So it takes a little bit of practice to get used to. All right, the last part here is the extreme value theorem. So let's see what this is stating. It says if a function f is continuous on a closed interval, so on a closed interval specifically, meaning we're including the endpoints, then f has an absolute maximum and an absolute minimum on that interval. So let's see what this means. First, let's give just a loose definition of what they mean by continuous. Basically, sort of informally, it means that there's no gaps or holes in the function. So no gaps or holes. And so we saw some functions that had holes in them here. They're not continuous. The function can't continue through that location. It has to skip it. So just visually, we can imagine a continuous function. It can be a curve too, but I'll just use a straight line for an example. This is continuous. If we're tracing a function out and we never have to pick up our pencil or our marker, then it's continuous. However, if it has a little hole, we have to like jump over that hole. Or maybe it's broken and we would have to skip to another location. So let me just list out those two examples. And there's different kinds of what we'll call discontinuities. So yeah, if it just has a hole in the function, we would call this a removable discontinuity. But it's not continuous. It's removable because it's just a hole. We could try to define the function there, and then it would fill in the hole in a way. But we might have something like this, where the function jumps. So we can call this a jump discontinuity. So two examples of a function being discontinuous, if there's a hole or if there's like a break, if it's broken. Continuity is a big theme in calculus. It's a core part of a lot of theorems and definitions. It's usually one of the first things you would consider is the function continuous. Um, and something we'll also consider here. So if a function is continuous on some closed interval, then this theorem is saying that we're guaranteed to have some absolute minimum or maximum. Let's just think of some random function, and I'm going to make it continuous. So I'm not going to pick up my pen. So maybe it looks something like this. So let's build a closed interval meaning like we're stopping and starting at a specific point. So we can't consider from negative infinity to positive infinity because those are open intervals. Oops. These are open intervals. So that's part of, in that case, we can't say we have a absolute maximum because there's always another point um, above it or below it. Same with absolute minimum. So we can't take that whole, we can't go on forever. We have to take some closed section. So let's say from like here to here. We can call this an interval. Well, since it's continuous, we can imagine this builds a little, like a little viewing box around it. Well, in this closed interval, in this little box, and it's continuous, so it means it can't jump around. Um, yeah, we have an absolute maximum here, and the absolute minimum looks like it would be towards the edge here. So give our max and our min. So that's if we're defining our interval like this, some closed interval. Let's pick some other random interval, maybe from here all the way maybe over here. Call this interval 2. So yeah, we can imagine how it slices the function, creating like a little box, a little window. This time, it looks like our absolutes will be on the edges. Absolute minimum, kind of close to this one, but it looks like it's a little bit lower, and an absolute maximum. So you can play around and maybe try to break this rule and see if you can come up with a counterexample. But they're stating it as a theorem. If we have some closed interval, so that's an important condition, then we're guaranteed to have an absolute minimum or maximum if our function is continuous. So that's pretty important to know. So you have some function you're working with. You don't know what it looks like, but you know it's continuous, and you have some closed interval that you're looking at. You're guaranteed to have some maximum and some minimum point. And that can be useful if you're trying to analyze a function, especially if it describes some real world phenomena. So just wanted to give a little demonstration of what this theorem is stating. And this theorem can be a prerequisite for some more advanced theorems or definitions. You can say, oh, since we're guaranteed to have a absolute minima and maxima, it must exist on this closed interval. All right, one more section here, and this is on the average rate of change of a function. And this will look a little bit similar to when we were looking at the difference quotient of a function. Remember, the difference quotient was essentially the slope between 2 points that are some distance h away from each other. Here we'll actually define some interval or some distance between the points. So let's look at the setup. So this is the average rate of change. It says if a and b, a not equal to b, so you're looking at 2 different points, we can say a and b, are in the domain of a function, then the average rate of change from a to b is defined in this way, and they define it as the change in y over the change in x. So f of b minus f of a over b minus a. It's really just the slope equation between 2 points. If we have, well, let's look at a drawing. Let's try it out. So let's say we have some function, and this will look pretty similar to our description of the difference quotient. So let's say we have some function and it looks something like this. Just to draw a random curve. And let's pick point A being here. So these will be in the domain, and let's say point B is over here. And these would be x values. Let's think of their associated points on the graph. If we plug in A into our function, the output we can describe as f of A. So this would be a point A comma f of A. And then similarly here, an x value of b. This will produce an output that we can describe as f of b, whatever we get after we plug it in. So this would be like f of b over here. Okay, and then let's imagine we have a line going through. And we want the slope of that line using these 2 points. We'll recall slope formula. If we have 2 points, x1, y1, and x2, y2. That equation was y2 minus y1 over x2 minus x1, if you recall from college algebra. We can do the same thing here. We have our 2 points. Now f of b is our y2 and f of a is our y1. B is our x2 and a is our x1. So let's just plug it in. So the slope here, y2 is f of b minus y1, f of a, over x2, which is b, minus x1, which is a. So that's the average rate of change. On average, how is it changing? Is it going up? Is it going down? We can view that as a slope. So this line that I drew, this blue line, you can call that the secant line of on a graph. It's a line that slices through the function at 2 points. So that's what they're saying down here, the slope of a secant line. It says the average rate of change of a function from a to b equals the slope of the secant line containing those 2 points, a f of a and b f of b. So it always helps me to see the visualization of this, to realize that it's just the slope formula between 2 points. And then we just made this general when we were viewing it as the difference quotient and just called this x and this x plus h. So some distance of h away. And then plugging that in, we got the difference quotient. So kind of multiple ways of saying the same thing. So let's find this for a few example functions. And I'll show you my process. So we're starting with our function. F of x is 3x squared. And it wants us to find the average rate of change from 1 to 3. So we're looking at this interval. They might give you an interval like this and say, find the average rate of change on this interval. We are looking at these 2 edge points. Those are your 2 x values. So let's first find f of 1. Let's plug that in. This would be 3 times 1 squared, which is just 3. So that means we have a point 1, 3. And then let's find f of 3. So we're plugging in our second endpoint. That's 3 times 3 squared. 3 squared is 9. 9 times 3 is 27. So that means our second point will be 3, 27. So the average rate of change will just be the slope between these 2 points. So I'll take my y2 minus y1, or we can call this f of 3 minus f of 1 over 3 minus 1, x2 minus x1. Oh, this should be a 3 here, sorry. Yeah, y2 minus y1. So 27 minus 3. So that will be 24 over 3 minus 1 is 2. 24 divided by 2 is 12. So that will be the average rate of change of this function from 1 to 3. Let's look at b. We'll do the same thing, but from 1 to 5. So earlier, we already found f of 1. Said that was 3. F of 5 would be 3 times 5 squared. So 3 times 25, which is 75. So let's do f of 5 minus f of 1. So 75 minus 3 over 5 minus 1. So that will be 72 over 4. And then we can just divide them each by 2 at least. So that's what, 36 over 2, which is 18. So just reducing in a few steps. Cool, let's look at C. Now we're looking from 1 to 7. We already know f of 1 is 3, so we've had the same starting point. Let's find f of 7. So that will be 3 times 7 squared, so 3 times 49, which is 147. So we'll do f of 7 minus f of 1, so 147 minus 3. So that would be like your two y-coordinate points over the change of x's, so 7 minus 1. So 147 minus 3 is 144 over 6. And if you divide that, you should get 24. So we're following that formula, f of b minus f of a. If we're looking at an interval from a to b, f of b minus f of a over b minus a can also be viewed as the slope between the 2 points a comma f of a and b comma f of b. So whichever kind of view, if you want to just think about the formula itself and find out what f of a and f of b is and plug it in, or if you want to think about it as 2 points and the slope between those 2 points. All right, I think there's one more here. So they give us a function. So this time g of x is 3x squared minus 2x plus 3. It wants us to find the average rate of change of g from -2 to 1. So we're looking at this interval. So -2 is our a and 1 is our b, if it's helpful to think in that form. So let's find f of -2. That would be 3 times -2 squared minus 2 times -2 plus 3. Right, well that's 3 times positive 4, -2 times -2 would be also plus 4, and then plus 3, that looks like 19. And then let's find f of 1. So 3 times 1 squared minus 2 times 1 plus 3. So that will be 3 minus 2 plus 3. Looks like positive 4. So let's find our average rate of change. That would be f of 1 minus f of 2 over 1 minus -2. So f of 1 is 4 minus f of -2. So 4 minus 19 over 1 minus -2. We can say 1 plus 2. So -15 over 3, which equals -5. So that's our average rate of change, but also equivalent to what we're calling the slope of the secant line. And that will be useful because part B is asking us to find the equation of the secant line containing these points. And that's what we found, -2, and we found g of -2. Oh, I'm calling it f here. Yeah, let me use the right letter. And then 1 g of 1. So those are our 2 points. We just found the slope between them. And if we want the equation of a line, well, we know what the slope of our line should be. We just need to build the equation. So there's different ways you can do it. You can plug it into slope-intercept form. I like to use point-slope form. So the point-slope form of a line, just to recall, that looks like y minus y1 equals m times x minus x1, where m is the slope, and you know one point on the line. We'll call that x1, y1. Well, we have both of those. Let's pick one of our points. Let's use the point, this one, where an x was equal to 1 and the output was 4. So 1 comma 4. And then our slope we said was -5. So in terms of our point slope form, this would be our x1, this would be our y1, and this is our m. So let's just plug it all in. So y minus y1, that will be y minus 4 equals m, which is our slope, -5, times x minus x1, or x minus 1. And I'll just turn this into slope-intercept form. So let's multiply this out and solve for y. So I'll say y minus 4 equals -5x plus 5, distributing the -5 through, and then I'll add the 4 over. Y equals -5x plus 9. That is the slope of the line, or that is the equation of the line going through those 2 points on our function. So the equation of the secant line. And then it asks you to graph. You can try plugging this into Desmos. That would be cool to see. Plug this in, visualize the graph, and then also this line. All right, so that was 2.3. We've been exploring properties of functions. So we started off looking at if a function is even or odd. So that's a kind of symmetry. If a function, so we can see it in terms of the graph or by plugging in -x into our function and simplifying. So that would be analytically using an equation. We talked about where a function is increasing or decreasing or constant, where a function would have local minima or local maxima, also where it has absolute maxima or minima, and then we were looking at the average rate of change of a function over time. There was another section where they have you just use a graphing utility to locate the maxima or minima of a function. So you can play around with that too. All right, that's it for this video, and I'll see you next time.